This is going to be a video on arc length and how the formula got generated. But before we do that, I'm going to show you my dog. Say hello, Grace. Hi, everybody. And she wants to play with her ball. Okay, so I'll probably have to break this couple of videos up into a series of videos just so I have the time to be able to make it, because each video can be a maximum of 10 minutes in length. So let me grab my notes and we're going to start to discuss. So we're going to do arc length and eventually we're going to get to surface area, but we're going to start with arc length first. So pretend that this line here is our function. And I'm going to try and zoom in a little bit. And what we're trying to do is we're going to try and approximate the length of this line using a line segment like such. We're going to do multiple line segments. Now, a couple of comments. Delta x is going to be constant. It's going to be a regular sized interval, which means each one of the delta x's is the same. Delta y will change based on the function length. And what we're going to be using is a as our approximate of the length from this piece to this piece. So that distance is being approximated by a. So what we're going to be doing is a modification of the Pythagorean theorem, okay? So let's just go back real quick. Delta x is going to be from xk sub k minus 1 to x sub k. And this delta y will be based on the kth interval. This will change, but this is going to be constant. All right. So now let's start thinking about the Pythagorean theorem. The Pythagorean theorem, now just remember A, that's the side we're trying to approximate. Sorry for the shaking around, my dog just jumped down. So the length of A is going to be equal to the square root, that's because of the Pythagorean theorem, xk minus xk sub 1, but that is going to be our delta x. This is going to be constant. Our y sub k minus 1 minus y sub k, well, that changes based on how the graph is changing. All right, so that is squared and that is squared based on the Pythagorean theorem. Okay, sliding over. So this piece here is going to become delta x. This piece here is going to become delta y sub k. This is not a constant value. It changes based on the interval that you're at. And remember, we still have squared and squared there. Okay. Now, I'm going to make a little comment. Notice when we look at this, we don't have a dx outside the square root. So we need to generate a dx. And that's part of the motivation behind what we're going to be doing next. We're going to come over here and we're going to factor out a delta x. So there's a delta x here, there's a 1 there, so notice I have the parenthesis, and I'm factoring out the delta x squared. If I'm factoring out a delta x squared, that's the same thing as dividing in this piece by delta x squared. So now I have this delta x squared, I have this delta y sub k, delta x squared, and if you think about what that is our delta y sub k over delta x squared, which will become our derivative. And our derivative of our function is getting squared. So it's underneath, it's 1 plus the derivative squared. Now you may be asking, where is this delta x coming from? Well, let's travel back, and we're going to see that we factored out this delta x squared. Now, square roots are defined over multiplication. So I'm going to take the square root of delta x squared. Well, the square root of delta x squared is delta x. Here's our delta x. When we apply the limit to the summation of this expression that we got here, delta x will become our dx. And so we're going to be taking the integral over our entire interval, the length of the line, when we take the square root of 1 plus the derivative of the function squared dx. Now note, the square root can cause some issues. So there are a few tricks. Well, there's really one trick we end up using a lot, and we'll talk about that in class. Let me scroll over here. We can orient to the y-axis as well, and so if we do that, the notation goes C to D rather than from A to B, and then it's still the same formula. It's just 1 plus g prime y squared. So we're taking the derivative of the function, and the function is not with respect to x, it's with respect to y, and then we have the dy. Okay, so just as an example, suppose we want to find the arc length of the curve of f of x is equal to x to the 2/3 between 0 and 8. So when we take the derivative here of this function, we get 2/3 x to the negative 1/3, which is 2/3, and the denominator has the cube root of x in there. There is a problem that we are dealing with, and that problem is with that 0. Am I allowed to plug 0 into that piece? This is something we always have to be concerned with. And plugging that 0 in, it's undefined. So we need to think about this differently. So what we're going to do, so instead of going this direction, what we're going to do is we're going to change our focus, and we're going to do the same function, but we are going to talk about it with respect to the other axis. So first thing we do is we need to figure out what 8 is going to become. We take y is equal to 8, we plug that in, and we're going to get that we get 4 out of that. So our limits of integration when we do this are going to go from 0 to 4. We're going to take the square root, and we solved our function for x. It was reading y